Hello. In this video, we're going to look at binary search tree questions in the programming assessment. I have over here ready to go the programming assessments that have been done up to today, and we'll just start looking through them. We'll start with this one. This question is asking for a function called total that will take a binary search tree and total up how many of the nodes in the binary tree have 2 children that are not null. Alright, before we look at that, let's make sure we understand the question. Here is a binary tree. Alright. So pause the video for a second and then count up how many do you think this tree has? What would be the right answer for this one? Alright, so how many nodes, number of nodes with 2 children? Alright, so why don't we go ahead and I'll highlight the ones. Does this node have 2 children? It does. We look at each one. This one does as well. This 22 has 2 children. This 33 has 2 children, and then no, this 33 does not have 2 children, doesn't have any children at all. And then we look over here, there's neither one of these. Leaf nodes don't have 2 children. We could have, let's get rid of this one. Okay, so then we also have like this 60 here, it doesn't have 2 children. Alright, so if we count up, we have 1, 2, 3, 4, 5, 6, 7. That's how many we have in this tree here. Alright, now the question is, how are we going to calculate this? If you look over to what I have given you before, there's a template for traversing a binary tree. We have the root node coming in, so when we start, we have this as the root right here. And then the way these always work is we want to look at myself, and then I want to do a recursive call to see what happens for each of the children. So if I'm at the root node, I just want to look at myself and and do I have 2 children? This does have 2 children. And then I just want to do a recursive call to add on to that whatever's on the right. And I don't do a loop for that, I do a recursive call. Let's see what that looks like. Okay, so this is for the November 13th, 2017A. Alright, and my recommendation was you have this template and then we'll modify it. Alright. The question was asking for a function called total. So we're going to use that. We're always going to look at, okay, we have a decision here. When we call this function in main, we would call it something like int x equals total of the root. And that's supposed to be the total for the whole tree. That should end up being this 7 for this tree. Alright, so what should the return type be? It could be an integer. Okay, and we want to do something with ourself. So if I have a root node and I want to see does it have 2 children, then I have this if test, and I have to go and look at the definition of my data type, which is here. I have a left pointer and a right pointer. So I check is the left pointer not equal to null, and the right pointer not equal to null. If they are, then I should count that as 1. So I'll have a count that starts off being 0, and if I have 2 children, count plus plus. Okay, then I do my left child and my right child, and what should this save value? This would be, I'll call this my count left. What I'm relying on is that when this function returns, it'll have the count from the left. So when I'm on the root, it should have the count from this whole left side, 3. And when I return from the right side, it will have the count from the whole right side, 3. Then what I want to return from myself is all of that added together. So count plus count left plus count right. That's the total for the whole tree. Other thing I have to fill in here is what happens when I get to null. If I call total with a null pointer, say I'm down here, the left and the right child of this node will be null. What should I return for the count? 0 is what makes sense in this case, because that doesn't contribute to anything. So this is the stuff that we'll have every time we have to have a base case. We have to stop recursing down the tree when we get to null. We have to do something with ourself. Do we contribute, yes or no? We look at the children. This is the answer from the children. And then we put it together. There's no loop because we're doing it with recursion. So this is what we're using instead of a loop. Don't put a loop in this problem. It's possible to do this with a loop, but you won't get it right. All right, that's one example. Now let's look at one that is, let's see, November 13th, A. So November 13th, A. Is that number 13th A or November 13th B? That was November 13th A, so that was A. All right. November 13th B. This wants to return the number of nodes in the binary tree that have exactly 1 child. Left or right is null and the other is not null. If we go over to my example, number of nodes with exactly 1 children, how many are in this tree? There's only 1, and it's this 60 right here. It has a left child but not a right child. Here, if we start looking at the root, we say, okay, I'm at the root. Do I have only 1 child? The answer is no, it has 2 children, so I wouldn't contribute anything to the total count. So I would have 0 plus whatever the answer is on the left, plus whatever answer is on the right. The code will look similar. You'll copy and paste, and you could pause and ask yourself, let me get it on one screen, what needs to change? Okay, the thing that needs to change is this if test, this part. We're still going to have 0 if we're null. We don't count a null node. And we're still going to add on the count from the left and the right to the root node and return that. But now I want a different if test. So I want exactly one of them to be null. So I either have the left is null, and the right is not null, or the left is not null, and the root right is null. So those are the cases. That's the only thing that changes for that one. Something to note here that people are messing up in the binary search tree and the linked list question. Anytime you have an arrow, you are dereferencing a pointer. So an arrow, this is just an aside, or a note. So root left is shorthand for star root dot. Okay, what does that mean? You go to whatever address root is, wherever that pointer points, and you look at the value. So dot is going to go look at the value in that part of memory. What if you have a root pointer? So if root is null, then root arrow is star null dot, and that is not allowed. You get a segmentation fault for dereferencing a null pointer. We're not allowed to go to that memory address. That means that anytime you have an arrow, or anytime you have a star root, you need to make sure that you're not null. In this function, this is what does it, the base case. If root is null, we return 0. So we know root's not null. Some people are doing things like trying to say something about root left data. That's a problem because root left could be null. If you want to do something with root left data, then you need to check to make sure it's not null. And we'll see an example where we need to do that. On this one, we don't. We just let the recursion take care of left. All right. We'll take another one of the problems. If you want to pause, you could pause. Okay, we'll go with this one. All right, so this one we have a different data. In this, we have a binary tree that has a string in there. So let's make an example that looks like that over here. And we'll leave this. Let's see, we'll get rid of maybe this. Maybe we'll put something here where we have a null. So on this one, the text is the word. It's the word field of the BSP node. All right. That's null. Null pointer. And then we put. Let's see. Are these in the right order even? All right, we'll have to put something else in here. Let's put some other stuff in here. I'll not make you watch that. Okay, now we have something that looks like a binary search tree. There's words here. Left is smaller, right is larger, except there's a possibility, so I want to check to make sure to see if any of the word items are null. So there I have one that's null. Maybe I have something over here that somehow got messed up. So really words shouldn't be null. But let's check. Alright, so this is asking for the number of nodes in the binary tree that have not null words. Alright, that's what it's asking for, so that's what we'll do. We'll go ahead and take this is actually going to be pretty similar, so I'll take this one as a starting point. And this is October 30, 2017. All right, we're supposed to do something called total. All right, what would be the count here? Number of not null words. 1, 2, 3, 4, 5. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 that don't have a null and 2 that do. That's the count that we want to figure out. All right, over, let's see, in here. So let's see. We want to return an integer that's a count. 0 is still a good base case, that when we get to these null pointers, null nodes, not a null word, but a null node, the whole node is null. We don't count that, there's no node there. We're still going to get a count from the left and a count from the right and put them together. Now what do we want the condition here to be? Alright, so we have root, and this is our data type here. What is our if test? So I want to check if root word is not null. And that's it. That's the answer to this one. Let's check out October 30th B. Alright, this one's a little bit different. This is asking for the combined length of all the words in the tree. Alright, at this point, why don't you pause the video. If you want, you can pause it on the question, or you can pause it on the answer to one of the previous problems. And now you try to do it. Take 15 minutes. What is the function? What do you need to do? So you pause it here or here. Okay. Did you pause it? Did you try to figure it out yourself? If you didn't, then pause it. Just watching all these answers isn't going to help you. You need to try it yourself. Alright, this is still called total. Now, let's go over and see what the answer would be for this one at least. Total length of all words. So we have moon, 4 plus 4, 8, 12, 17, 22, 27, 33, 37, 43, unless I added or counted wrong. And these with null values don't add anything, they don't count. Alright, over here now, instead of counting based on whether word is null or not, I really want to count based on, I really want to do count equals the string length. This is C, so you get the length with string length. Okay, but we already see there could be an issue. This could be a null pointer, so we really only want to do that if the word is not null. This goes under the advice of before you use a pointer, you have to check that it's not null. So the string length does actually go and use that pointer. It looks at whatever is at that address, whatever character is there. And so there you go. Here we have the string length at the current node. We're going to add on the result from looking at the whole left tree and the whole right side of the tree. And then we add them all up and return that. Alright, let's take another one. We'll go to November 27th, A. Okay, this is asking for printing. So this is printing data. There's no return value, but it's telling us to print all nodes that have a data item. Here we have an integer that have a data item smaller than some parameter. All right, let's see. We'll go back to the integer example. So data items that are less than some particular value. Let's say 40. So which ones are less than 40? All right, less than 40. We've got 30, 22, 33, 15, and 23. I didn't say whether they need to be printed in any particular order, so who knows? Those are the ones that need to get printed. All right, so the way we're going to solve this is the same pattern. We're going to look at the whatever node we're at some root node to start off with. Do we need to print myself? If I'm at 50, I don't need to. So I take care of myself, I don't have to print 50. And then I do the recursive call to take care of my left subtree and my right subtree. Let's take this as a starting point. So this is November 7, 2017. So I'll get the header. Let's see, this is going to be smaller print. Doesn't have to actually return anything, so it's going to change some things inside. There's supposed to be another parameter, call it value. Alright, I'm going to ask you to pause the video here, or here. Okay, so you want to pause the video here, or here, and work on making this function. So pause it, take 10 minutes, write down what you think should happen. Alright, now we're going to go and fix this. Remember, we're supposed to print the node, print the word, let's see, print the value. Here we have integer values. Alright, we're printing these integer value only if it is less than whatever the parameter is. And the way that we would call this in main, we would say something like smaller print. The pointer we have to the root and maybe 40. So that would be supposed to print all values that are less than 40. Alright, so for our base case, we just return. There's nothing to return, there's no counts. The base case is a null pointer, a null node is nothing, so we just don't do anything. Alright, now we want to do something with our data, and our data is called data here. So we're looking at data, and we're either going to print it or not. So however we want to print, this would print the data, and what's our if test? Supposed to be checking if the data is smaller than the value. Alright, now we want to have the children take care of themselves, but they're not returning anything now, so you don't have to save the result. And that would be it. You have to have a base case where you stop. If it's null, you just stop here. Do something with myself. If I'm smaller than the value we're checking, I'll print, and then have the left and the right. Now for this one, I didn't specify the order. We have three things here. We have myself, we have the left, and we have the right. So depending on what order we put our code here, it'll print them in different orders. The question for you, with this the way it is, self, left, right, on this tree, what is the order that they get printed? All right, and you could go through and trace it through. First we go to 50. We don't print that, and then it calls its left. So we would be at 30. 30 calls itself. It prints 30. All right, we print 30, and then we call left. According to the code, the way I have it right now, we call left. So then we'd be at 22. 22 gets printed and calls its left. 15 prints itself, calls its left. There is no left there, so that'll be a null value that it just returns. So it does actually go into smaller print with a null value, but then right away I return. The right of 15 is also null, so it returns. We're back up at 22. 22 had printed itself, and now the left side of 22 has already been done. And the next thing that happens in where we're dealing with the 22 node, so in the 22 node we finish the left, now we're going to do the right. Then we do the right, and that's 23. Alright, then the 22, the whole subtree at 22 is done. That means we would be at the 30 node. The 30 node took care of itself, and now its left subtree is done. It would go to its right subtree. So then we would be at the 33, which gets printed. And 33's children are both null. Things stop there. These are all the values that get printed, and that would be the order. That is called, well, whatever. You can, yes. That is called some order of traversing the tree. So your options there are you have self, left, right, or you could do left, self, right, right, self, left. So the question for you is what order to do 1, 2, and 3 to print the values in increasing order. All right, what order do you want to do these, to print them in increasing order or decreasing order, or top of the tree first order? Okay? All right, little extra for you. Let's take this is it then, that's done for that question. Now let's look at November 27th, B. All right, November 27th, B. Now we have two integer parameters, and we want to print if the value at the node is between the two. This is similar to the question we just did. So what you want to do is take a pause on a separate piece of paper. You want to write down what's the prototype for the function. So what does it return, and what are the parameters? Okay, now I will give my answer. November 27th, 2017B. Okay, it's supposed to be called range print. It doesn't say that it's returning anything, so void range print. There is a parameter that's the binary search tree node pointer, and two integer parameters. So int val1, int val2. Alright, so that's your prototype. Now we're supposed to print everything that's in this tree that has data between val 1 and val 2. And we have root, the items we have is root data, that's something, root left, and root right. Take a pause, finish the function on paper. Okay, now we'll go ahead and put it in. First thing to take care of is our base case. If we are a null, then we are not a node and we should just return. Alright, and then let's take care of myself. So if my data is in between these two ranges, I haven't specified whether to use less or equal to. We'll go ahead and use less or equal to. Let's say it's greater or equal to val 1 and root data is less or equal to val 2. Then I'll print the data. Alright, you could, if you wanted to, you could check handle if, say, val 2 is less than val 1. I wasn't so concerned about that on this question, but so most people, if you did it correctly, they also handled, that would be just another case if they're out of order. So this is assuming that val 1 is smaller than val 2. Alright, so I do myself, and then I do the children. Range print, root, val, let's see, root left. Val 1, val 2, and range print, root right, val 1, val 2. Alright, this is an instance where we have the root that we have to pass through. We have to have a pointer to whatever node we're looking at right now. And then these parameters, we would call it something like range print, the root of the whole tree, and maybe we want to do everything between 10 and 100 or something like that. Alright, and those parameters have to get passed along into the function when you do the recursive calls. Some people were trying to do something like range print root left. That doesn't work. Range print needs 2 more parameters. And so you just pass the parameters along to the recursive calls to the function. Alright, let's go with we do one more here. December 6th, A. Alright, here we have the data again. And it's going to return 1 if there are no repeats in the tree. None of the data items are the same. So depending on the rules, we could have in our tree two nodes with the same value. So you're either allowed to have repeats or not. We haven't specified in the problem whether repeats are allowed. So maybe we want to check the tree to see if there are any repeats and then do something with them. Okay. First, what is the prototype that this is asking for? What are the parameters and what is the return value? So you may have to pause, read the statement again. This is December 06, 2017. Okay. Alright. It's asking for return of 0 or 1. That's an integer. So all different. We have the root pointer. And there are no other parameters. I'm going to call it in name something like all different roots, and maybe I would say if they're not all different, then something. Okay. Now, base case. Base case is going to be if root is null, we're going to do something. We have to do something with myself, and I have to do something with left and right. Put that all together. Okay, so what I want to do with myself in this case is I want to look at just the neighborhood around me. If I'm right here, I just want to look at myself and my children. Is it the case that myself and my children are all different? Okay, so am I different than my children? All right, so what is an if test for that? So I have my data. So I have my data. I have a left and a right potentially. Let's look at the left. So if the left is not equal to null, and I can write this condition one of two ways. So if the left is equal to my data, then what? Left is not null. Let's see, root left data. So the data on the left, here I am, I'm calling this right now, this is the root. If I'm down inside the recursive call somewhere, root left data. If those two values are the same, then I was told I'm supposed to return 0. So I can return 0, I don't actually have to do anything else. So that's looking at myself. Just looking at myself, I'm not different than my left. I should also check my right. And I can put this together in one if statement to make sure that my logic is right. Keep those parentheses there. So if my left is not null, it's the first case. If the right is not null, then I should look at that the same. Left is not null. If the date is the same, return 0. If the right is not null and the date is the same, return 0. That's looking at myself. So if I happen to get past here, made it past if, then it's okay at this node, right? This node checks out all right, and now I need to look at the left and the right. So how do I call the left? I call all different root left. And I'm going to put this into an if test. So if the left is okay, and the right is okay, then I'll return 1. So I sort of did the left and the right and put it together all in one if statement. All right, now what about this base case? When I get to a null node, should I return 0 or 1? If I'm at 15 here, is that different than its children? It is different than its children. There are no children. So the 15 should return a 0. If it calls its left, it would be looking here, all different left, all different with a null pointer. If I don't, the way I have the code right now, I want this 15 to return 1, then my base case needs to return 1 as well. So an empty node is different than its children. So it's convenient to think of it that way because it makes this work here. And that would be it. So I'll say also note that all works only if PST is correct, in sorted order. Right? If we have the case that a 15 could randomly show up over here, then the code here won't work. We'd have to do something else. All right, but if we have a binary search tree that's valid, it's in order, then it is true that if each node is different than its children, then the whole tree will be all different than each other. All right, let's take a look at B. This one is asking for all the same. It's similar. I'm not going to do it. You can do that yourself. So we'll leave that for you to do. All right, so if you want to look at this stuff, let's see, note a few pictures are in this document. All right, and this file is in U1 Junk Programming Assessment. If you are an ISU student with an account on the CS server, then you can look at this document if you want to. Otherwise, you have to go back and pause the video. All right, so advice for you now is, all right, go back, and these questions are all there as well in UJunk Programming Assessment. Those are PDFs. If you have an account on the system, you can get those. Go back and look at each one of those. Don't look at the video. Go back and look at each one of those and fill out what you think the answers are on paper. Right? Do it from memory. You have to think through. While thinking through it, it helps probably if you draw a picture of a binary tree. All right, and then go and check the file to see if your answers make sense. You could have, some things could be slightly different. You could do some things different that would still be correct. You always have to have a base case when you're doing recursive stuff. There has to be a base case. There has to be a point where you check for a null pointer. You always have to do something with yourself. You always have to check the data for yourself. Depending on what you're doing, you're either checking the data item that's in there, or you're potentially doing something with the left and the right pointers. So this one was doing something with the left and the right pointers. You're always going to do something with yourself. You're always going to have a base case. You're always going to have a recursive call to the left and to the right. Okay, and it's just how we put all that together is different depending on what we want the function to do. If we're returning a value, so if we're returning some kind of value, then when you do the recursive call, you have to save that value. If you just do total root left, suppose it computes some value and it happens to compute the correct value and return it. If you don't save the value here, it disappears. So you have to have that value saved and then use it. Right, the way you're thinking of this is that you're at some node in the middle of the tree. That's what this root is. It starts off being the root of the tree, but then in the middle of executing, it's some node in the middle of the tree, and you can ask for the solution to the left subtree, the solution to the right subtree. You look at yourself, what it looks like right here, put that all together, return it. So then whoever called you can use that. It always needs to be the case that if you dereference a pointer, you need to check that the pointer is not null. That's something else that always needs to be the case. You always have to check that it's not null. All right, that is it for binary search trees. Good luck.